So this is the last video of linear kinetics chapter. So we start with the mechanical work for this video. So this is not chemical work from the food you eat. It's mechanical work, which is from the force and displacement. So mechanical work is defined as force applied against a resistance, which means we need a force to define mechanical work. And then work can be quantified by multiplying force and displacement. So multiply these two actually. So again, we have water bottle here, water bottle. So I can apply a certain amount of force to this water bottle. Okay. If my force is larger than friction, I will be able to move this water bottle. It moved, right, from here to here, which means it changed its linear location or linear position from here to here, which is linear displacement. Once you get force applied and the displacement moved due to by the force applied and multiply these two, then will be quantified mechanical work. So the force and displacement, and one more, okay, cosine theta, cosine theta. So theta means angle, angle between force and displacement. And then right here, so we have a box here. I want to move this box this way. So but my force acting diagonally upward. If my force is larger than friction, you can move this box this way. Which means this is the direction of displacement, the direction of force, and then this angle between this force and direction and the displacement vector. We need to apply this cosine theta. I can show you why. Okay. So when we move the box again there, okay, force here, and then displacement, angle theta here, theta, and displacement. Since the box will move this way, horizontally, okay, we only need horizontal component of this force. This force, as you learn, can be broken down into two perpendicular components. This horizontal and then vertical component. Okay, this vertical component of this force has nothing to do with this work calculation. That's why we only need what? These horizontal components. So that by multiplying cosine theta, so we'll be able to delete unnecessary information which are not needed for this work calculation. Okay, so we'll go over more question, go over this on more about this one soon. Bottom line is we need to apply the angle between force and displacement to calculate the work calculation. And then this is scalar quantity. But I want to highlight this one. Let's look at these two components to calculate mechanical work. Force and then linear displacement. Force is actually vector quantity. And then linear displacement is also vector quantity. Vector, but the result will be scalar. This is something you have to be careful of. Okay? So again, if I ask you whether work is scalar or vector quantity, you have to put work is scalar quantity. We can work is scalar quantity. And the unit is joule, okay, joule. Actually, unit of force is Newton, okay? Unit of displacement is meter, so Newton meter. But this is equal to the unit of torque actually. But sometimes two different quantities can use the same unit. But in order to avoid some confusion, so instead of using this one, I'm going to use the joule for the unit of mechanical work. And the example of mechanical work here, so weightlifting. So upward lifting and then downward lifting. So assume that you are doing some sort of the barbell curl. It's a barbell. And the weight of barbell is 5 Newton. Lift height 0.5 meters. A force is given and the displacement is given. So upward, okay, this motion. Okay? Force is acting upward and displacement is also acting upward. So that I can multiply force will be this one, 5 on the Newton, right? From Newton. Work, mechanical work will be force times displacement 0.5 and cosine theta. Here angle, how much angle between force and displacement? Since they are acting in the same direction, angle will be 0 degree. and cosine 0 is equal to actually 1. Actually 1. Answer will be 250 joule for this one. For this one. How about downward lifting? You're moving downward this time. So you're moving downward. Which means direction is acting downward. Like displacement of direction is acting downward. Still your force is acting upward. Acting upward. If then angle between force and displacement will be how much? Actually 180. So cosine 180 will be negative 1. So therefore this one answer will be negative 250 joule. 250 joule for upward and downward, negative 250 joule. Okay? Due to the angle between force and displacement. Okay. Still, as you learn, work scalar quantity, but still you will be able to have positive work and then negative work. Okay. But in here, in mechanical work, the sign, which is positive or negative, that does not mean the direction of the mechanical work. It just means energy generation or energy absorption. That's why you can still have the sign or positive or negative for mechanical work. Although this is scalar quantity. And then positive work or negative work, as I mentioned, you can get the positive or negative work. Okay. And after this one, you determine by the angle between force and displacement. If this angle is less than 90 degrees, okay, which means F and D, force and displacement, they are in the same direction. So we get the positive work. But if this angle is larger than 90 degrees, for example 100 or 120 degrees, then these two are in the opposite direction, so negative work. You can actually test this one. You can insert any numbers in your calculator. For example, angle is 85 degrees, okay? Which is less than 90 degrees. Should give you positive value. And then if you insert, for example, 150, it's larger than 90 degrees, which will give you negative the value. And then once you figure out the signs of mechanical work, and then you can relate that work to the axial muscle contraction. So if you get positive work, which means this theta is less than 90 degrees, and then there's related to concentric contraction. As you know, concentric contraction means your muscle fiber gets shorter. And if you get a negative work, which means this is related to eccentric contraction, like an eccentric contraction, your muscle fibers gets longer. And your force, displacement, they are acting in the opposite direction. And then no work means you are not moving. You are generating force, but you are not generating any displacement, which means this isometric the contraction. So once you figure out the signs of work, you can relate that information to the muscle contraction. And then mechanical power. And then this is related to the work. This is coming from actually the work. So definition-wise, this is a rate of work or intensity of work. So once you figure out mechanical work, we will also be able to figure out mechanical power, because this is a rate of work or intensity of work. Now this one will tell us how can quantify mechanical power. So pure work means mechanical work. Once you get this one, divide this value by time elapsed. Simply, okay? The work divided by time elapsed will give you the power. Okay? And the work is, as you learn, force times displacement times cosine theta. Okay, as you learn. Okay? So but here, from the linear kinematic chapter, you learned velocity is equal to displacement times displacement over time elapsed. That's why this one, can be reorganized this way. So d over delta t will be velocity. So force times velocity. Okay, so actually these two are the same. So you can use either this or this to calculate the power. And the unit of power is watt, W equal to watt. And this is also scalar quantity. Like mechanical work. Work was a scalar quantity, right? As you just learned. and then scalar, times scalar, then the power will also be scalar. And the example of the power, so this is from your textbook, stair climbing. So total number of steps is 30 steps here, okay? And each step has 25 centimeters high, okay? Height of each step is 25 centimeters. And then the participant who is moving upward, climb up to the stairs, so 550 Newton, his body weight. And the time taken from bottom to top of the stairs, so 15 seconds. And then I need to calculate power, mechanical power. This is important for your exam. You'll see very similar questions to this one in your exam. So power, as you learn, okay, force times displacement times cosine theta, and then delta t, okay. So in order to calculate again power here, so we need to have all this information. Okay? Then we got force here, right? 550 Newton, and then displacement. So in order to calculate displacement, actually, here displacement is actually height, right? From bottom to top of the stairs. So 30 step for height or displacement. 30 step times 25 centimeters. Because each step has 25 centimeters high. So that is 50 centimeters, which is equal to 7.5 meters. Okay. And the work. So here F is 550 times 7.5 meters times cosine theta. Here angle between force and displacement will be the 0 degree, because he is moving upward. At the same time, the force acting upward too. That's why angle between force and displacement in this question will be the 0 degree. So cosine will be actually 1. So 1. So multiply 550 by 7.5, okay, which will give you mechanical work. So once you get this one, divide this one value by time left, 15 seconds, okay, which will give you power. So calculate H first again, the number of steps, and then here the height of the one step. Multiply these two, just 7.5 meters. You got displacement, and the force is from his body weight, okay? And then angle is 0 degrees, so again cosine 0 degree will be 1. And then divide this one by time elapsed, taken from the bottom to top of the stairs. Okay. So in order to calculate power, we have to calculate mechanical work first. So simply divide this one value with time elapsed to give you mechanical power. And then mechanical energy. Next concept, mechanical energy. It's capacity to perform mechanical work. Is the ability to perform mechanical work, which means mechanical energy is highly related to the mechanical work. Okay, which means in order to do mechanical work, we should have mechanical energy. That's why they are using the same unit, but they are highly associated with each other. They are kind of interchangeable. So what was unit of work? Unit of work was joule. That's why unit of energy is also the joule. And then work was scalar quantity. That's why also energy will also be scalar quantity. And then in the mechanical energy, there are two different types of mechanical energy. Two types: potential energy and then kinetic energy. So potential energy means energy due to vertical position, which is actually height, vertical position. And then kinetic energy is energy due to the motion, or velocity. There are two different types of mechanical energy: potential energy and then kinetic energy. And these are due to vertical position. These are due to the object velocity. So they can quantify potential energy. Here EP means potential energy is equal to M. Mass times G means 9.81, gravitational acceleration. And height. Okay, height here. These are due to vertical position. And kinetic energy due to motion, which is velocity. That's why all velocity components must be involved in this calculation. Here E means kinetic energy is equal to 1/2 times mass times velocity squared. This is how equation that you can use to quantify kinetic energy. So potential and kinetic energy. Here, that's why ME means mechanical energy is equal to potential energy plus kinetic energy. We must add these two to quantify mechanical energy. So we cannot use just one of them, but both of them must be involved in mechanical energy. Here again, E means mechanical energy, so potential energy plus kinetic energy. So I'd like to introduce a very important concept, which is called conservation of mechanical energy. Again, conservation means something remains constant. Mechanical energy remains constant under certain situations. For example, if the gravity is the only external force acting on a system, mechanical energy remains constant. Actually, in the human body, we can have two important external forces. Okay, one from, although we cannot feel them, okay, we can have two primary external forces acting on the human body, although we cannot feel them. One is actually gravity. So external forces acting on the body, gravity. One is gravity, and then the other one is ground reaction force. Remember this, right? Ground reaction force. So as long as you have contact with the ground, you are supposed to get the reaction force coming from the ground to your body. There are two external forces, but here, in this situation, if the gravity is the only external force, which means we are not having this one. We have only this one. If then, mechanical energy remains constant. But in what situation can you get the no ground reaction force? Okay, as I mentioned earlier, you're supposed to get this force, okay, as long as you have contact with the ground. Which means if we don't have a contact with the ground, for example, if I'm in the air, I don't have contact with the ground, right? Then I'm not supposed to get ground reaction force. Which means in order to meet this principle, okay, I must be in the air. If then I will get only gravity as a source of external force acting on my body. Okay, keep that in mind. Again, energy equal to potential kinetic energy is constant if I'm in the air, which means I'm gonna get only gravity as a source of my external force acting on my body. Let's go over one example of this conservation of mechanical energy acting on the body. Okay, so here we have diving example. The platform here, and he's about to dive into the water. Then there are three positions here. Position 1, 2, 3. So 1, 2, 3. So for example, at position 1, if he's standing on this platform, okay, standing on there. So what kind of the mechanical energy does he have? He has only one. He's not moving there. So he has only one potential energy at here, but he doesn't have any kinetic energy because he is not moving. So she's standing. And then position two. Now he's jumping. Okay, jumping into the water. When he's in the middle, in the air, right here, he's gonna get kinetic energy as well as potential energy because this one has a certain amount of height as well as he's moving toward the water. That's why he has both kinetic energy and then potential energy added up will be the mechanical energy. But right here, the water level, he is gonna get only what? Kinetic energy. There will be no height. That's why potential energy will be equal to each other. So he will get only kinetic energy. So here he has only potential energy. He has both kinetic and potential energy. He has only kinetic energy here, right? And then as he moves down, potential energy will decrease because height will be decreased. But as he moves down, kinetic energy will increase due to gravitational acceleration. Potential energy will decrease and kinetic energy will increase by the same amount. Because he's in the air. which means he is maintaining the same amount of the mechanical energy based on conservation of mechanical energy principles. That's why all mechanical energy at these 3 points are equal to each other. Okay. Then let's go over one more example of conservation of mechanical energy here. Okay. So ball drop. Okay, ball drop. You have ball here, and just let it go. It will fall down, right? Fall down. And then I want to calculate the velocity at here, at the ball impact, right before the ball touched the ground. Okay, so holding the ball, so let it go, and then get the velocity right before the ball touched the ground. Okay, so when the ball is here, I'm holding the ball right here. If then, what kind of mechanical energy do I have? Does the ball have at this point? At here. Okay, the ball has only what? Only the potential energy. Because ball was not moving, just I'm holding the ball. So the ball has just potential energy here, and then when ball was here, what kind of energy does the ball has? The ball has only what? Again, kinetic energy, because there will be no height. So why? The ball has only potential energy here, only kinetic energy here, and then these two energies should be equal to each other. This means here, energy at release right here, energy impact right here. As I mentioned earlier, energy here, the ball only has potential energy, okay, at the top, and then when the ball was here, the ball has only what? Kinetic energy, and then these two are equal to each other. So then mgh, when the ball at the top, is equal to kinetic energy. So m can be gone, and multiply it by 2gh v squared. Okay, then the square root of 2gh to v. Okay, so the square root of 2 times 9.81 times height is 1.5 meter, which will give you velocity at the ball impact. Because I will leave this to you. People usually calculate to obtain this velocity value. The bottom line is, mechanical energy remains constant if the object is in the air, which means the object will be receiving gravity on the source of external force. And then here, mechanical energy versus work versus mechanical energy. So as you learn, mechanical energy is capacity to the mechanical work. So you can relate these two. Do you remember the relation between impulse and linear momentum? So as you learned, impulse, right, causes linear momentum. Okay. Here, change in linear impulse causes change in linear momentum. So change in linear momentum means change in final linear momentum minus the initial linear momentum. It's a change in linear momentum. Impulse causes change in linear momentum. Same thing, very similar concept to this one. So work causes change in mechanical energy, like impulse causes change in linear momentum. So work causes change in mechanical energy, which is equal to change in kinetic energy plus change in potential energy. Okay? Like this. Impulse causes change in linear momentum. So let's go for an example of this relationship. Okay. Again, we are going back to diving example. So we have one diver here, but I would like to calculate here the work done from 1 to 2. When he moved from here to here, how much mechanical how much mechanical work done? Okay. When he moved from here to here. Okay. He just changed his vertical position from 1 to 2. So as you just learned, mechanical work causes change in mechanical energy, and then change here, work causes change in mechanical energy. This one is a change in kinetic energy plus change in potential energy. So since he just changed the vertical position, okay, he only get what? Change in potential energy. This is mgh. So by applying this equation, so we'll be able to calculate the work done from 1 to 2. And then the last slide of this linear kinetic chapters, the ball catching. We have a baseball situation. Look, this is from your textbook. And then the mass of ball is provided, 1.3 kilogram. And then the ball's velocity is also provided, 40 meters per second squared. And then you need to calculate, okay, now how much mechanical work is required to catch the ball. Okay? And the ball is traveling at a rate of 40 meters per second squared. And then we have pitcher here and catcher. And pitcher just throw the ball, okay, this way. And ball mass here, as you just saw there. And then ball's velocity right here. And then in here, we have one assumption that the vertical position of the ball remains the same. Which means although the ball is supposed to move, something like this. Assume that there's no vertical position, no change in vertical position of the ball. Which means the ball moved straight. Which means here work causes change in energy. Change in energy means change in kinetic energy, a change in potential energy. And then here, change in kinetic energy means 1/2 mass final kinetic energy minus initial kinetic energy. How about this? Change in potential energy. Final potential energy minus initial potential energy. But here, since h, height, remains the same, these two are the same. So it can be gone. You don't have to worry about this. So in this question, to calculate how much work is required to catch the ball, can be calculated by the change in kinetic energy. Because work is equal to the change in energy. So by using this, we can quantify how much work is required to catch this ball. Here, so final kinetic energy minus initial kinetic energy. Mass is, but here final velocity is 0 meter per second because the ball will be caught, right? Then this one will be 0. So this one can be gone. Okay, then in this question, work is equal to, so negative 1/2 mass V1. M is 1.3, okay, squared. Don't forget squared, sorry. And then V is a 40 squared. 1/2 times 1.3 times 40 squared, which will give you total amount of work required to catch this ball. Okay, so we are done with the linear kinetic chapter. So again, this linear kinetics means linear plus kinetics. So all these quantities are used to explain the linear motion.